You have probably been using large language models, aka LLMs, every day now, right? I mean, who isn't? These models are truly amazing. They are so great that sometimes we start thinking they are capable of doing absolutely any knowledge-based activity. However, have you ever asked one of these models to plan a complex schedule for you? If you have probably noticed something interesting. Tools like ChatGPT, Claude, or Gemini are great at multi-step reasoning, writing and generalizing across a wide range of domains. But when it comes to solving planning problems like creating work schedules, optimizing delivery routes, or organizing game tournaments, these AI tools still fail miserably. It is not that they are dumb, it is that planning itself is a completely different kind of problem. In this video, I want to show you why LLMs struggle with planning problems, and more importantly, what other tools you can use to solve them. We will unpack three things together. First, what makes planning problems so special. Second, why LLMs simply aren't built for this kind of tasks. And third, how combining them with traditional mathematical methods can give you the best results. By the end of this video, you will gain more clarity about the limitations of LLMs, and you will walk away knowing exactly which tools to use when real planning is on the line. Alright, so let's dive in. So, what exactly is a planning problem? Well, in simple words, it is about deciding who does what, when, and how, under a bunch of constraints. Technically speaking, it is an optimization type of problem. That means we are trying to minimize or maximize something, like cost, time, or some resource usage, while respecting certain rules. In math or code, you can think of it like this. Minimize total completion time subject to no overlap, resource limits, precedence constraint, etc. And that is basically saying finish everything as fast as possible, but don't break the rules. And these problems show up everywhere, usually hidden behind the scenes. For example, vehicle routing, deciding optimal paths and schedules for deliveries to minimize distance or cost. Maintenance scheduling, which is about determining service times for machines to minimize downtime while meeting operational constraints. Or job shop scheduling, which is about sequencing interdependent manufacturing operations to minimize total production time. Or employee rostering, which is about assigning shifts to staff while satisfying regulation, availability, and workload balance. Every one of these problems sounds simple until you try to solve it for real. And that is when you realize that one small change can explode the search space from thousands of possibilities to trillions of them. And that is why, in computer science, most planning problems are considered NP-hard. It means that the number of possible combinations of solutions candidates grows so insanely fast that even the best algorithms that we know are incapable of finding the best solution within a reasonable amount of time. So, for the really difficult planning problems, instead of looking for the perfect solution, we have to look for the good enough solution that satisfies most of our constraints. Now, let's talk about how to get to those solutions. Before large language models, we already had powerful methods to handle planning problems. We refer to these methods as mathematical optimization. It is a family of techniques for finding the best possible combinations of variables that minimizes or maximizes an objective function fx, possibly subject to a set of equality or inequality constraints. The development of optimization techniques has been the focus of interest of mathematicians for centuries. Fermat gave us the derivative, Lagrange gave us constraints, Gauss gave us data fitting, Damsling gave us algorithms, Nesterov gave us speed. Here is how it usually works today. First, you model your domain, the entities, resources, and tasks. You define constraints, the rules that cannot be broken, and then you run a computational program that implements a mathematical solver to find the optimal solution. Examples of mathematical exact solvers include Google's OR tools, which is a software suite excellent for vehicle routing, scheduling, and linear programming. IBM's iLog, CPLEX, which is a commercial optimization studio used in logistics, finance, and manufacturing for large-scale optimization. Or MiniZinc, the tool that I used when I was studying at university, I can still remember, which it is a modeling language that works with multiple solvers. And MiniZinc is great for constraint satisfaction problem. Well, it is important to recap here that both mathematical and meta-heuristic based systems don't try to think like humans as most AI algorithms do. These tools search systematically and exhaustively through enormous combinations until they find the best valid configuration. Now, let's talk about LLMs. Large language models, or LLM, are deep neural networks that have been trained using self-supervised learning to predict the next word in a sequence of text. And to do this, these neural networks have learned during training from massive text datasets at the scale of the entire web corpora, or what can be considered our collective consciousness. And all of this is thanks to the transformer architecture, which is the T in GPT. Remember, the G means next word prediction, and P is from pre-trained. The simple goal of predicting words in a sequence gives LLMs an astonishing power when it comes to understanding human language. They can summarize, generate a lot of text, and even chat like humans do. And differently from humans' brains, LLMs have incredible memory capabilities. They can recite entire books, chapters, word by word without any problem. So LLMs can replicate almost any written style, explain technical topics, and are particularly good at writing source code. LLMs can now search over the internet, plan steps using a technique called chain of thought, or COT, which is basically iteratively refining the answer with better prompts to make it better. They can also call external APIs and perform tasks with context awareness. So there is no doubt, LLMs are improving very, very fast. But here's the thing, even with all that power, LLMs still cannot solve planning problems effectively. I mean, they can describe a plan, simulate a plan, or even sound confident about the plan, but they cannot compute one. Let's talk about it. Why can LLMs handle planning problems? In simple words, LLMs cannot solve planning problems because they don't properly search for all the possible solutions. Instead, they guess what would be the best move forward based on the training data they have. They have no built-in concept of an objective function or problem-specific constraints. So if you prompt an LLM, it will be able to explain you what a valid planning schedule should look like, because that information is already encoded into its neural network, but it cannot actually find the best solution, which is also original through mathematical optimization for you. Now, imagine that you have the following employee rostering problem. You have 30 employees, 5 work dates, and 5 shifts per person. That is 150 shift assignments with rules like no overlapping shift, respect time off, cover all rules, and stay under 40 hours per week, for example. When you ask an LLMs to generate that schedule, it will do it for sure. it will output something that looks convincing, but if you look closely, then you will see that some rules fall apart. For example, someone could work 2 shifts at the same time, another has no week off, or some coverage gap appear. And the reason is that scheduling isn't a simple sequence of decisions. It is a global optimization problem, and every change affects the entire system. So in the previous example, if you have 30 employees and 150 shift assignments, for the first shift, you have 30 options. For the second, the number of options is 30 multiplied by 30. And for the third, is 30 at the power of 3, and so on. So in total, there are 30 to the power of 150 options. And that is really an enormous number. For comparison, it is a number with 141 more zeros than the total number of atoms in the observable universe. And this happens because for the LLM, they don't evaluate the entire search space. They predict what looks right next. And that is the core issue here. It is impossible to optimize billions of combinations by guessing the next word. This probabilistic process leads to an accumulation of errors over long sequences. In any sequential task, a small error early on can lead to exponentially larger errors later. Even with a high per-step correctness rate, the probability of a correct plan for a long sequence can drop to nearly zero, and research has shown that merely fine-tuning LLMs on a corpus of planning instances doesn't lead to robust planning skills. Think of it like a complex Rubik's cube. You can fix one side easily, but doing so usually breaks another side. Planning is the same. The optimal solution emerges only when you evaluate all sides at once. Reasoning-oriented models like GPT-01 or Gemini Pro 2 now, they can sometimes handle small cases for you. For example, a 7-day schedule with a few employees. However, let me say it again, once you scale it up, their reasoning collapses because they cannot manage the combinatorial explosion of possibilities. And you may think, well, what's about other forms of machine learning? And the answer is no other form of machine learning works here, simply because there are no labeled examples of optimal schedules to learn from. Every company, every factory, every airline has its own constraints, which is data that cannot be generalized or reused. So no matter how smart a model seems, if it doesn't explicitly search, score, and respect constraints, it won't solve real planning problems. Now, here's the thing. Just because LLMs cannot solve planning problems exactly, that doesn't mean they are useless. LLMs can play a supportive role in hybrid AI systems. Let's talk about it. LLMs are excellent at structuring and communicating information. So instead of optimizing the plan themselves, they can translate the messy human-written requirements into formal optimization models, generate constraints automatically, like for example, employees can work 2 consecutive night shifts, create data pipelines that feed solvers like Timefall or OR tools, or interpret and explain the results of solvers to a non-technical audience. In other words, LLMs can act as assistants to traditional optimization engines, not as replacements. This pseudocode over here can give you a good idea of how this works. Here you can ask the LLMs to describe each state, propose a new plan, compile the plan into a submodel with fixed variables, and then let the solver verify and improve the current solution. So the best AI systems today use this division of labor. The LLM handles reasoning, communication, and setup. The mathematical solver handles the heavy lifting, the actual optimization. And that combination is what is driving the next generation of intelligent scheduling, logistics, and resource allocation systems. So, generative AI and particularly LLMs are incredible. They can code, write, reason in multiple steps, and explain. However, LLMs still have some limitations, as we have seen in this video, and planning problems is a representative example of it. These problems belong to a different world, the world of mathematical optimization and search algorithms, not the world of next token prediction. LLMs cannot reliably solve planning problems because their token-by-token generation is a probabilistic process, not a logical one. And this leads to errors that accumulate over long sequences, an inability to guarantee correct outcomes, and a fundamental lack of logical reasoning required for complex planning tasks like scheduling or routing. So if you are building an AI system, remember, use LLMs to assist in the process, but let the mathematical solvers do the heavy lifting computation. Use the right tool for the right thing, because when you learn how to get the most of each and every tool that you know, that is when you will become really unstoppable. Thank you for watching. See you in the next one. Bye.